So we see problem 6.2 on the screen now. The key difference between this problem and the previous problem is that now the state is a vector valued variable instead of a scalar variable. So the cost in this problem is still an infinite horizon Lqr problem, but the cost, instead of simply x of tau squared plus rho u of tau squared d tau, now we have q and r here, where q has the size 3 by 3 because the state is a 3 by 1 vector, and r is still a scalar because the input is still a scalar, and the output is also a scalar because of this c. It's a single input single output system, but the number of states is 3. The key motivation here now is to get a feeling for tuning the matrix Q, and in this case the scalar R. Typically when we have multiple inputs, R is also a matrix of size m by m, where m is the size of the input vector. Another important lesson coming out of this problem is to see that we can use the Lqr problem, which is essentially a regulator problem. What I mean by a regulator problem is the following. We assume that the initial state is not zero, and then we pose a cost of this form, and then we want to minimize for non-zero initial conditions this cost. Note that if the initial condition is already 0, we would have 0 cost, because x dot would be a times 0, and then 0 input would make x dot 0, and then the x will stay at 0 for all times. So this is essentially a regulation problem or a stabilization problem, in which the initial condition is not considered to be 0, and we don't have any external references to track. And one aspect of problem 6.2 is to see that we can use this to design or tune a controller by tuning the control variables Q and R and obtaining a state feedback gain F, and then using it in the form of this loop to solve a tracking problem where we do have inputs R. Yeah, so there is really not much more to say about this problem. Maybe one last thing is to talk about the closed loop. You can see that the closed loop for this problem can be derived as follows. So we have x dot equal to ax plus bu, and we have y equal to cx. Now u is typically just f of x for the Lqr problem, or the of course, and the initial conditions are typically not 0. So this is what we usually have for regulation problem. Now we have u is equal to and therefore the closed loop would be this one. So yeah, I suggest that you try to play with the MATLAB code and try to understand or get a feeling for how to tune these gains Q11, Q22, and Q33. One thing to note here is that the output is just the first state. So because your cost should represent what is the most important for you, you might observe that you get good tracking performance when you set Q11 higher than Q22 and Q33, because if Q11 is higher, what you're essentially saying or essentially telling the optimizer is that I really want my state 1 to go to 0 as soon as possible, or in other words, state 1 not being at 0 is extremely expensive for me. And yeah, you can try to play with these weights and get a feeling for the tuning parameters. That's basically it for this problem. I would be happy to discuss with you if you have any specific questions about this problem, or if you have any interesting observations, some peculiar stuff that you found while tuning these matrices Q and R. Okay, so that's it for this problem. Thanks a lot.